Um, it is really awesome. I mean, some of the pictures and definitely some of the contents I have also taken from there. Um, Definitely do that. Second question, using B1 and B2, can we recreate Alice qubit state? No, no, we cannot. Because see, Alice's qubit is in the superdense coding, Alice's qubit is part of the entangled state. So we cannot just create part of the entangled state using some classical information. That's not possible. In the after event bit sharing, does it happen in classical channel? So uh, is this about dense coding? So in dense coding, if what we are doing is that we are sending one the qubit that is with Alice, and Alice is sending that to Bob. Definitely sending a qubit cannot happen over classical channel. It will have to be something more than that. It can be teleportation itself. It can be something else which we do not really consider too much in dense coding, but it cannot happen over a classical channel. Definitely. Yes, everything in the IBM Quantum platform is available for free. Okay, let's share once more and let us start with the CHSH game. So, this is a game where we are, this is kind of a game that, as I started by saying in the beginning, that Einstein kind of questioned that everything that you are saying, perhaps it is not because quantum is like this, perhaps because there are some hidden variables in the theory that you are not aware of. So quantum mechanics is not complete. If quantum mechanics were complete, if you knew about those hidden variables, then you can actually, there will be no measurement collapse, no probabilistic nature, none of those will be there. Everything becomes deterministic. Um, so it's kind of that famous quote that Einstein told, that God doesn't play dice with the universe. And apparently Bohr told him that don't tell God what to do with the universe. Um, so this game is something that Bell first came up with. So his name is used in the Bell state and all. Bell first came up with and was later uh, actually modified and slightly improved by, I have forgotten the four names here, sorry. Um, they kind of improved it and gave a game theoretic view of this. The idea here is that Alice and Bob are in two different rooms. And as you can see, there is no communication allowed between them. There is a bar. So Alice cannot talk with Bob, Bob cannot talk with Alice. There is a referee who are interrogating both of them. Now, the referee will send some questions, X and Y, to Alice and Bob respectively. They will be zeros and ones. Alice and Bob will reply back with A and B. A and B will also be zeros and ones. Now, Alice and Bob can win this game only if this happens. So when X and Y is 0, 0, A should be equal to B. X and Y 0, 1, 1, 0, for all these three cases, the answer that Alice gives should be equal to the answer that Bob gives. But if X and Y are 1, 1, so if the referee sends 1 to Alice, 1 to Bob, then the answer of Alice and Bob should be different. This is the criteria that they can win this game, Alice and Bob. And as we have seen that there is no communication between Alice and Bob, so it is not possible that Alice and Bob can receive the question, discuss amongst themselves, and then decide what should be A and what should be B. So they cannot decide their answer after looking into the question. So it's very easy to argue. What would you do if you were here? If I were here, definitely I would say that let's always decide that, okay, I will talk with Bob and I will decide what the A and B values are, then they will be equal. This is the strategy that I would have taken if I were here in place of Alice and Bob, because then out of these four cases, on three cases, I will definitely win. but I will lose here. But on these three cases, I will win. So it is very easy to argue that if I use a deterministic classical strategy, that say I will always answer 0, Alice will always answer 0, Bob will also always answer 0. If this is my strategy, then I can win 3/4 of the time, but I cannot win more than this. So I can win only with a probability of 75%, not more than that. And you can give a more mathematical argument to this and show that okay, it need not be just the A and B both need not be 0 0. You can do all these algebraic stuffs, and you can show that okay, whatever deterministic strategy you take, if you win these three, you will always lose this one. So this is easy. I mean, we need not go into this too much mathematical. You get the idea that what will happen here. What I will not go into here, there is a long calculation that you can do, that what if Alice and Bob apply a probabilistic strategy, that okay, I will not decide that I will always answer 0, but I will use some probabilistic strategy that is classical. Maybe I'll toss a biased coin or something, and depending on the outcome of that biased coin, I will answer. Even if they use this kind of strategy, they cannot win the game with probability more than 75%. So nothing you do classically, now no classical strategy you can apply that will allow you to win this game with probability greater than 75%. Let's see whether quantum can help here. So what will happen before Alice and Bob goes to the interrogation rooms, they will prepare and share a Bell state between themselves. So yeah, I mean, in terms of game, this can sound very awkward that okay, I have been asked by the police that oh, you come, I am going to interrogate you, and I'll say no, stop, I need to talk with Alice and I need to create a Bell state, before you start asking me questions. This can sound very funny or silly, but this is how it will go, that Alice and Bob will share a Bell state before entering the interrogation room. What good will this do? So now Alice will measure her qubit in a particular basis, Bob will measure her qubit on a different basis, and this measurement will depend on X and Y, the questions that they receive. And based on the measurement outcome, Alice will give the answer A. If the measurement outcome is 0, Alice will give answer A equal to 0. If it is 1, Alice will say A equal to 1, and same for Bob. This is the strategy that they have taken now. So just recall something that we kind of emphasized before, that Bell state remains entangled in every spin direction. Irrespective of the basis in which you measure the state, it remains entangled. There are some small mathematical stuffs, but it's okay. I mean, you don't have to remember everything here. That I will call such a state psi theta, which is cos theta 0 plus sin theta 1. I'll call such a state psi theta. If you look into this kind of state, say this is Alice's state where some alpha value of the angle, this is Bob's state for some beta value of the angle. If you take the inner product with the maximally entangled state, and if you do some calculation, it will become cos alpha minus beta by root 2. The inner product is always this. And I will define a unitary u theta, which looks like this. And you can write it like this. What does it mean? If you want to understand physically what it means that if you take a state psi theta, it will map it to the state 0. If you take a state psi theta plus pi by 2, it will map it to 1. But as I said, it's okay. I mean, you don't have to remember everything to understand what is going to happen. Just remember this u theta thing here, that it's cos theta sin theta minus sin theta cos theta. That's all. So now the quantum strategy is, if Alice gets the question 0, so remember Alice is getting questions X, Bob is getting question Y, both of them are either 0 or 1. If Alice gets 0, she will apply U0. So again, this was my U theta. So U0 would just mean that you apply theta equal to 0 here. If Alice gets question 1, she will apply pi by 4 on her qubit of the entangled state. Similarly, if Bob gets y equal to 0, he will apply pi by 8. If y equal to 1, he will apply minus pi by 8. So after this change is done, after Alice and Bob apply these unitaries on their qubits, they will measure on the 0-1 basis, the computational basis, and whatever the measurement outcome they get, they will answer that. The measurement outcome will always be 0 or 1, right? So let's look into this. Xy is equal to 0, 0. So remember what will happen. The point was that for xy equal to 0, 0, 0, 1, 1, 0, Alice and Bob should have the same answer. And for xy equal to 1, 1, Alice and Bob should have different answer. So when xy is equal to 0, 0, Alice applies u0, Bob applies u pi by 8. This is what we discussed here, that when both of them are 0, Alice applies 0 and Bob applies pi by 8. So they apply this, and if you now calculate what is the probability of outcome for each of these cases, AB can be 0, 0, AB can be 0, 1, AB can be 1, 0, AB can be 1, 1. So when does Alice and Bob win? When the outcomes are same. So on this case and on this case. These are the two scenarios. If the answer is 0, 0 or if the answer is 1, 1, they win. So what is the probability of that? It's this plus this, which is 2 plus root 2 by 4, which is roughly equal to 85%. Similarly, if xy is equal to 0, 1, then also Alice applies u0, Bob applies u minus pi by 8. Same again, that if the answer is either 0, 0 or 1, 1, they win. So what is the probability? You add these two, it is roughly 85%. Now let's come to 1, 0. Again, same thing. If it is 1, 0, Alice and Bob should again have the same answer. And they apply the unitaries accordingly. And you see that the probability is 85%. Fine. All of these was great. Where we got stuck, 1, 1. This is what was giving us the trouble in the classical case, where Alice and Bob should have different answer, not the same answer. So now when x and y are 1, 1, I get u pi by 4. Alice applies this, Bob applies this. Now Alice and Bob should have different answers. So 0, 1 and 1, 0. These are acceptable answers. You add these two, you get the probability of 85%. So all the four cases, the winning probability is now roughly 85%. Previously, we argued that the winning probability is never greater than 75%. But by using this kind of strategy, we are able to get a probability of 85% here. What does that mean, basically? So we were able to find a scenario where sharing quantum correlation can provide a higher probability of winning, right? If whatever we use classically, a deterministic method or a probabilistic method, we were getting stuck at 75. Here we are getting 85% probability of winning. So this is definitely higher than the classical strategy. What it shows is that this quantum entanglement, when I was sharing the quantum entanglement, I could have used a biased coin, and that's what I said, right? It can be a probabilistic approach. I can use a coin, I can throw a dice, I can do many things, and depending on their outcome, I can decide what my answer will be. But although we didn't go into the mathematical rigor, none of this that gives you more than 75% probability. So quantum entanglement is doing something more than classical probability. When I share quantum entanglement, I am able to get something more than what only classical correlation was giving me. So a local hidden variable theory is not sufficient to explain what is going on in quantum mechanics. So you can ask 2 or 3 questions here. You can ask, how did you get those angles, pi by 4 minus pi by 8? You can, I can mold your question in a different way, and say that, okay, can you use some other angles? You used 0, pi by 4, pi by 8, all these angles. You showed you can do it with probability 85%. Can you come up with some other angles which will help us win the game with 100% probability? Yes, and I see most of you are saying no. Yes, the answer turns out to be no. So there is something called this Seidelson's inequality or Seidelson's bound that shows that irrespective of any strategy that you take, you cannot win this game with greater than 85% probability using a quantum system. There is something very interesting that is called a PR box, that is beyond quantum. If you can share something like a PR box, you can win this game with probability 100%, but PR box is not compatible with theory of relativity. It violates that theory of relativity. So as long as your quantum strategy, which respects the relativity theory, you are using something like that, you cannot win this with probability greater than 85%. And this particular experiment on CHSH inequality was awarded the Nobel Prize in 2022. And here is something that I learned from my teachers about this when we were discussing up after this 2022. I was in doing my PhD back then. So one of my teachers, maybe you have already heard of him, Guru Prasad Kaur. So he told us something very, very interesting. And this is something extreme. I found it very interesting. What we just argued is that if you share a quantum correlation, you can go beyond classical. So a classical process cannot mimic a quantum process. So this is what we argued. But when you are experimentally doing this, when you are actually creating some correlation, so you see the reason that he actually could think of this, there are certain physicists who still think that quantum mechanics is not complete, and there can be some super quantum theory or something that will be complete. So the question here is, what if nature is not quantum? What if nature is some super quantum, which we still don't know about? So when I am creating a correlation in nature, if nature is not quantum, if nature is super quantum, then the correlation is actually becoming super quantum, even though I don't know about it. I don't know the theory, but nature is super quantum. So it is creating some super quantum correlation. So when I create this correlation, I do the proper change in, I apply the proper unitary, I collect the experimental data. All of these was collected from nature. Now, it is also possible that nature is not quantum, it is basically classical. That can also be a possibility. But the fact that I am collecting data from nature and it is following the CHSH probability, it definitely proves that nature is beyond classical. It may be quantum, it may be super quantum, it may be some other theory that we have not yet discovered. It is definitely not classical, because collecting data from nature, I was able to, not me, so these guys were able to go beyond the probability that classical theory offers us. So, so it's the CHSH inequality that was given a Nobel Prize is not interesting just because it kind of experimentally proved this game, but it's also interesting because it experimentally proves with like probability, or it deterministically proves with experiment that nature is beyond classical. It is quantum, it is beyond quantum, anything else, but it is definitely not classical. So yeah, I'll stop here. Um, so what we covered was some, what I tried to cover today was to show what is entanglement, some protocols that we can do using entanglement that couldn't have been done classically. That's teleportation, that's dense coding, and the CHSH inequality, which shows like that there is no classical method which can mimic what a quantum correlation can do. So yeah, I hope this was useful. You found it interesting. And if there are any questions, we can take that. I'll definitely share the slide with you. Okay, so I see one thing that the IBM Quantum Learning Platform, I don't know who showed yesterday, but yes, the IBM Quad platform has migrated to IBM Cloud. Everything that was in the learning platform is still retained, so you can see everything. But if you have already seen an older version of IBM Quantum Learning Platform, the interface is no longer the same. Um, if you want the latest, let me try. I can give that to you. Just give me a second. I can give you the latest version. Okay, just let me share the screen once more. And so this is the new IBM Quantum platform. It is in cloud. So you should create an account here. If you already had an account, that's great. In the previous thing, here are all the tutorials and everything. So here you see documentation of Qiskit. These are all the learning courses and modules that I was talking about. You can look into tutorials. All of these are now here. This is what you should be looking at. This is the upgraded version. So I can share this on chat. Okay. Um, Yes, so okay, let's come to some of these. Still new developments. Yes, so you see, I am not from a pure theoretical physics background. So there are definitely a lot of works are ongoing in this direction, but perhaps I am not the right person to tell you what the latest things that are ongoing here. Quantum strategy probability. So, okay, so this is an interesting question. Whether the probability using quantum strategy is always greater than classical? No, you need to find the proper angles. So, what Bell did was the angles that I showed, he found the angles. And if you can properly find the angle, you can beat classical. Those are not the only angles that can beat classical, but if you end up selecting very bad angles, you may not be able to beat the classical system. But what this shows is that it is possible to have a strategy which will beat classical. Okay, so in simple terms, quantum entanglement simply means that it's a two qubit system where if you measure one qubit, the other qubit which may not have been disturbed by anyone, which may be in a different lab or something, the state of that qubit will also be changed. So in some sense, they are physically separated, but there is some correlation retained between them so that some disturbance on the first qubit hampers the other qubit. I hope that helps to think about entanglement. What is the difference between 00 and 11? Okay, I am not sure I followed this question. So if this is in terms of classical bits, it is like two bits can give you four possible information. The first bit is 0, second bit is 1. So in that way, 00 would mean that first bit and the second bit, both of them are 0. Even quantum mechanically, it would mean the first bit is in qubit 0, the second qubit is in state 0. 1 would mean the first is in 1, the second is also in 1. But I'm not sure if that is what you were asking for. Again, I am not sure what you mean that can't we regain our designs already implemented? So sorry, what does that mean? I'm not very sure if you can please. So the free access is again for 10 minutes per month, but again, 10 minutes, I would always encourage that please use it. 10 minutes is a lot. Uh, Use it. It is perhaps not sufficient to do all big experiments, but it is still sufficient to get you started. So please use it. Okay, this is a very interesting question, and I'm not sure I can immediately answer on top of my head. What is the trade-off between teleportation fidelity and Bell inequality violation when using non-maximally entangled states? And can a critical threshold be established where teleportation remains reliable despite submaximal entanglement? My one-word answer to this will be no, because if you use a non-maximally entangled state, you cannot create a orthogonal basis to measure. If you cannot create an orthogonal basis to measure, then what will happen is, sometimes you will get some outcome. There will be sometimes when the outcome of the state is completely like unknowable. So if that kind of thing happens, you cannot do reliable teleportation, but obviously with some probability the teleportation will be reliable. I'm not sure what this means. That please share demo video. Yeah, if you can please explain. I'm not sure I follow this. Yes, only 10 minutes per month will be provided. If you take the state 0, 1 and measure in the Bell basis, you will have 50% probability that you will get 5 plus, and with 50% probability you will get 5 minus. Any one of those when you measure with 50-50 probability. But when observed, it change instances or states. Again, sorry, I am not sure I follow this. Yes, when you, if this is about an entangled state, when you observe it, if you observe a single qubit, it will change the state of the entire system, and for both the qubits. Definitely not today. I cannot give a demo of quantum machine learning in Qiskit. But yeah, I don't know how the QTs are going. Maybe in some other QTs there will be something like this. So yeah, please follow on. So after creation of account, you get 30 days trial. No, as far as I know at this point, you still have 10 minutes free, but eventually you may have to put in some credit card number just to be sure that whoever are creating this account are actually serious and not just putting in more and more accounts. So again, if this is but what when observed it changes instances or states, then how probability works here. So if it is something like 1 over root 2 0 0 plus 1 over root 2 1 1, then you get 0 with probability square of 1 over root 2, which is half. So that's how the probability works here. You can have a state like 1 over root 3 0 0 plus root 2 over 3 1 1. Then the probability of getting outcome 1 1 is 2/3, whereas the probability of getting outcome 0 0 is 1/3. So the coefficients still dictate, um, the probability, but yeah, the outcomes depend on the state. Any applications developed using CHSH game concept? Yes, there are some cryptographic protocols developed by Eckert and others who use the CHSH game concept to detect whether there are some eavesdropper or someone. So this is actually there. So both the websites offer same options. Do you mean the old IBM Quantum platform and the new one? The old one has been sunset, so please follow the new one. I would encourage you. There is a question that in Qiskit 2.1 transpiler process also changed. If I want to work on previous version backend.run, I would encourage, see, one thing you can do is install older versions of Qiskit, but I would encourage you to not do that. Use the primitives, the sampler or the estimator. Don't use backend.run, because there are a lot of more things that you can do using Qiskit primitives that you cannot do by using backend.run. And at some point, the backend.run will be deprecated and totally removed from Qiskit. So it's better to remain updated instead of using. Not immediately. So if you implemented older versions of some, I mean, if you implemented some circuits using older versions, immediately you cannot do it. But there are some Qiskit code migration projects that are ongoing, which we hope we can make public sooner than later, which can help you to migrate your old codes to newer versions without you having to spend a lot of time on top of that. In classical, you can get a maximum of 75% probability of winning. Okay, this is an interesting question, that how does interaction with the decoherence affect an entangled state? Can entanglement survive in noisy environments? It will depend on the nature of the noise. Um, Say for example, you are there is a thermal relaxation kind of noise, so there is a probability that your 1 goes towards 0. Then there is a high probability that the state 1 1, if you measure after some times, it some of the part has decayed towards 0. So entanglement may not survive in noisy scenario, but there can be certain noise which can still preserve entanglement. For example, if the noise is local unitary, then definitely entanglement will preserve. If it is something like the T1 noise, which is not really unitary, then entanglement will not preserve. No, so here is a question, that in classical we have 0 or 1 to describe system with yes or no, whereas in quantum state with 00011011. See, when I was looking into 00011011, it was a 2-qubit quantum state. So if we look in, because entanglement cannot be there for a single qubit. So if I look into a single qubit quantum state, then it's like something like alpha 0 plus beta 1, which is in some sense, I mean, it is not mathematically rigorous if I say this. In some sense, it is both 0 and 1 at the same time. On the other hand, in classical, you can have either 0 or 1, not both of them at the same time. Uh, Next question is, does it mean no optimal solution using classical? We can get optimal in quantum. I won't say like that, because in classical you are getting 75%, that is optimal for classical. In quantum you are getting 85%, that is optimal for quantum. So how you define optimal, if you say how you define optimal, if you just say that something is greater than the other, then it is optimal, then fine. But if you say that I want to win this game with 100% probability and that is my optimal, then even quantum cannot do that. YouTube link of what? Sorry, there was a question, please share YouTube link. Sorry, is there any shared PPT? I'll share it. I'll share the PPT. So there is a question, can we use these IBM Quantum Link and Quniverse for research paper? Definitely, you can run your experiments in one of those and you can write a research paper using the results that you get. Okay, so there is a question, is it true that the time travel between Alice and Bob doesn't depend on their separation? So there is no direct time travel between Alice and Bob, and that's kind of the point, that um, you kind of need to do classical communication. So there is no really faster than light communication between Alice and Bob. Of course, if you are talking in terms of how much time it will take to send the classical bits from Alice to Bob, that will definitely depend on their separation. Yeah. Okay, this is a very interesting question. Can weakly, I mean, I think you mean a non-maximally entangled state ever outform maximally entangled states in specific noisy teleportation channels? I don't know. I don't know the answer to this. Again, my question will be how do you form a basis? But since you are talking about noisy channels, you can argue that maybe the maximally entangled states are also not perfect here. This can be something that you should try out. I would strongly encourage you to try this out and see. I don't know the answer to this. I don't know if there is an immediate answer to this. Not just that I don't know if there is a known answer to this. IBM Quantum Learning. So wait, IBM Quantum Learning is a website. There is no installation there. If you are talking about installation of Qiskit, all you need to do is a pip install Qiskit, or just go to the Qiskit YouTube channel. You will find an entire set of playlist for Qiskit videos, and it starts with how you install the software up to how you do the most advanced stuff in there. So yeah, please look into that. So this question, is it possible to tune or update states or instances to produce desired result for certain application or logics? If I understand the question well, it is definitely possible. That is what any algorithm is. That is what quantum algorithms are. That you kind of define your steps in such a way that the probability of getting the desired answer is very, very high. So definitely that is possible. Will eavesdropping attack on part of entangled state, we can consider it as a local operation? It is not that simple. So I am not really an expert in quantum cryptography, but the little bit what I studied during my PhD, what I understand is that using the idea of monogamy that I was talking about, that a maximally entangled state cannot get entangled to any other system. Using this kind of information, you can actually detect Eve. So that's possible. If I have an n bit, can use the Q teleportation to transfer my bit to another person using code for two different parties. Yeah, so if you have n bits and if you share entangled states with, say, n other parties, you can always teleport um, one bit to one party using the first entangled state, second bit to the second party using the second entangled state. That is definitely possible. Can we design a quantum teleportation protocol leveraging non-locality without entanglement to bypass certain Bell inequality constraints? Once more, I am not sure about this answer, but just by thinking in terms of what these are, um, it may not be something very similar to this entanglement, even if it exists, because the way the entanglement works is that you measure in Bell basis and you get one of the Bell outcomes. So if that kind of measurement outcome procedure is still there, I am not sure whether it's possible, but I don't think I can rule it out here also. Oh, YouTube link of this session. I don't have it. Maybe, yeah, I see Professor Aswath is here. Maybe Professor Aswath can share later. Oh, okay. Great that you are working with Anupama. Yeah, I'll hear it from Anupama what you are doing. Sure. Okay, so this is something interesting that Is the following understanding correct, that if psi is equal to a0 plus b1, then a square is the probability that it is in state 0, b square is the probability it is in state 1, where a square plus b square is equal to 1? Yes, it does not say that the qubits are in 0 and 1 simultaneously. You are right. So when we say that the qubits are in the state 0 and 1 simultaneously, it's a bit of a misnomer. What it kind of says is that it's a complex state that does not happen classically. It is something, it's a state which is beyond classical. It is definitely, mathematically speaking, not 0 and 1 at the same time. But the reason I guess most of us say that is because it's easier to understand. And the second thing is that when you measure, it collapses to 0 and 1, assuming you are measuring in the computational basis, 0 or 1. But what you have written here is completely correct. It is not 0 and 1 simultaneously. It's a completely different state that has no equivalence in classical. So anything that I say classically is not sufficient. How many max qubits are input to circuit? So that will depend on your problem. At this moment, IBM has 156 qubits. That's the largest you can go at this point. Entanglement happens between two states can happen in many ways. So say two qubits came together at some point, they interacted, and the interaction can make it entangled. If you want to see it in terms of circuit, what you can do is you take two qubits, apply Hadamard on the first qubit, then C naught from first qubit to the second qubit. And then if you measure, you will see that the state is actually entangled. You will get 0 with 0 0 with probability 50%, 1 1 with probability 50%. Is it possible to make use of IBM platform for the simulation of urban flooding runoff generation? Okay, I'm not very sure I follow this, but if this is some research problem that you can formulate as a quantum problem, you can definitely use Qiskit or anything. You can definitely use Qiskit or anything to solve that. What physical properties can be entangled? Spin polarization are famous. Any other criteria to check for possibility of entanglement? So, this is a very interesting question. There are different ways to check entanglement. What we showed here was very simple, but yes, there are things like entanglement measures, entanglement witnesses, all of those things are there. So, you can use those techniques to check for this. Again, I won't say that I am very sure about this. Any limitations in quantum teleportation using entanglement over classical? I'm not sure there is a limitation, because classically you cannot um, convey, I mean, you cannot send a quantum state classically, but this is something that you can send one quantum system from one lab to another lab. So there is, I don't think there is a classical equivalent to this. So um, I'm not very sure if there is an immediate drawback of this. I see Priyanka Gupta has her hand raised. If you want to unmute or just write in chat. So, okay, so the same question, that the above equation A0 plus B1, it mathematically speaking, it does not mean it exists in 0 and 1 simultaneously. When we say it's a superposition, to be mathematically rigor, it says that it is something um, beyond 0 and 1. It has no classical equivalence. So there is nothing that you say or I say classically will be able to exactly represent what superposition is. It is something beyond zero, it is something beyond one. It's a different state that is not found classically. So the nearest thing that we can say is that it is both zero and one at the same time. This is again a very interesting question whether entanglement is really necessary for computing. I don't think there is an immediate answer to this. Recently, there was some, no, not very recently, 2 to 3 years back, there was a paper which kind of showed that entanglement may not have a lot to play when it comes to quantum machine learning kind of problems, but they didn't give an immediate answer. So don't think that I am just saying that entanglement is not required for quantum machine learning. On the other hand, there are certain kinds of problems, like the query algorithms, perhaps you have seen, their quantum entanglement becomes very important. um, if you think of error correction, entanglement is necessary because that is how you have the original qubits versus the ancilla qubits, and you kind of measure the ancilla qubit, and you get the information of what is there, what is the noise in the original qubit. So yes, definitely in that sense, entanglement is important. It will depend on the problem domain. So there is another question. Even when we drag and drop gates in IBM's quantum composer without connecting to an IBM processor, the measurement shows an entangled state. Are the results of combination of virtual gates hard coded in simulation? Yes. So that's how simulation works, right? That you kind of hard code those things, and that is why you cannot simulate beyond, say, at most 32 qubits. If you want to go to actual simulation of nature, then you have to go and use a quantum computer. You cannot just say that I'll use a simulator to do something which is not possible to do classically. What you have written here is exactly correct, that it is hard coded. So it is kind of mimicking a quantum computing. It's not really quantum computing when you are doing simulation. Okay, I guess, yeah, if there are no more questions. Sorry, I cannot hear you, unfortunately.
Hello, am I audible, sir?
Yeah, yeah.
Yes. So thank you, sir, for this wonderful session and patiently handling all the questions in the chat. Uh, Once again, thank you. Just a request, please share the PPT on the
Yeah.
fdp.academy email ID so
Okay.
we can share it on the canvas in the module.
Sure, sure.
Thank you. Thank you so much, sir.
Thank you. Thank you.
And just an announcement for the participants, we will having a quiz on July 17th, 24th, and 31. So we are going to have 3 quizzes based on the session that we are the session that will be conducted on this days. Thank you. Thank you so much.
Thank you.
Thank you.